So in the previous section, we gave a conceptual idea of how to find probability using a normal distribution. The normal distribution was just a curve that had a bell shaped that was symmetric about its mean. The area under that bell-shaped curve represented a probability. So it was either the percent of a population who had a specific characteristic, or the probability that a randomly selected individual from the population would have that characteristic. In this section, we're going to talk about how do I actually calculate those and put this into context. That's going to require us to develop something called the z-score. That z-score can be related to something called a percentile. In particular, we're going to use those z-scores and try to relate them to what we're going to call a standard normal curve, and then utilize all of that information to find the value of a normal random variable. So the first thing we're going to do is interpret and determine z-scores. The z-score represents the distance that a data value is from the mean in terms of the number of standard deviations. We find it by subtracting the mean from the data value and dividing this result by the standard deviation. There is both a population z-score and a sample z-score. Depending on what information you're given, it varies the formula a little bit. The formulas do look different because in the first one with the population, we have parameters where we were looking at the population mean mu and the population standard deviation sigma. Very rarely will you actually know this information. We'll mainly use this formula as we get comfortable with the methodology. As we start the section on inference, we will use sample information to try to infer something about the population. We will end up using the sample z-score much more. Note that mu is the population mean and x bar is the sample mean. Sigma is the population standard deviation and S is the sample standard deviation. So in both cases, we're taking the x value, we're finding its difference or its distance from the mean. So we're subtracting off the mean, either the sample mean or the population mean. And then we're dividing that by the appropriate standard deviation to see how many steps we're taking away. Remember when we were drawing our picture of the normal, I said that the standard deviation we could think of as the step size. It's where how much further out we should put each tick mark on our number line. And that's because I wanted to relate it to this z-score. The z-score is unitless, so there's no, I can't talk about the z-score being pounds or ounces or inches or feet or anything like that. There is no unit associated with it. It does have a mean of 0 and a standard deviation of 1. So as an example, let's say that we had the mean height of 20-year-old males, 20 years or older, is 69.1 inches with a standard deviation of 2.8. And the mean height of females 20 years or older is 63.7 inches with a standard deviation of 2.7. It wants to know who is relatively taller, Kevin Garnett or Candace Parker. Well, what do we mean by relative? I want to know, how does this height of 83 inches relate to the average height of 69.1 inches when I'm looking at step sizes of 2.8? And to come up with the relative height here, I'm going to compare this height of 76 inches to the average of 63.7. I'm going to put that in terms of a number of steps by dividing by 2.7. So essentially this idea here is I want to know who is relatively taller my definition of relatively taller means who is more steps away from the mean than the other. So we're going to calculate z-scores. So for Kevin Garnett, we're going to take his height minus the average height of 69.1 and divide by 2.8. So Kevin Garnett's height was 13.9 inches above the average. In terms of a step side of 2.8 inches, that gives me almost 5 steps above the mean. Candace Parker, on the other hand, her height is 12.3 inches taller with a step size of 2.7. So when we look at the number of steps we would have to take away from the mean, where each step had a size of the standard deviation, it would only take us 4.56 steps to get out to her height. So his height, Kevin Garnett's height, is relatively taller than Candace Parker's height because his is more steps away from the mean than hers is. This is what I mean by measuring the number of steps away from the mean. We took the observed value minus the average and divided by the standard deviation to get a number of steps. In order to go further with probability, because we're going to be talking about the percent of the time something happens, we need to define what we mean by what's called the percentile. The percentile, the kth percentile, denoted P sub k, is the value such that k% of the observations are less than or equal to the value. So for example, if I look at the 98th percentile, that means 98% of all of the possible values will happen below that point. Only 2% will be above that. Same way with the 99th percentile. It means 99% of all people in the population will fall below that point. Only the top 1% will be above that value. It should be noted that the median represents the 50th percentile, right? The median is the middle of my set of data, so 50% of the data lies to the left and 50% lies to the right. So it fits into this idea of a 50th percentile. So let's interpret a percentile. The GRE is a test for admission to many grad schools, and the Graduate School of Public Health requires a GRE score no less than the 70th percentile for admission into their Human Genetics MPH or MS program. Interpret this requirement. What does the 70th percentile mean? That means that 70% of the people who've taken the test will score less than that value. So the 70th percentile means that 70% of individuals who took the exam scored worse and 30% of the individuals scored better. In order to be admitted to this program, an applicant must score as high or higher than 70% of the people who took the GRE. In other words, they must be in the top 30%. So we're now going to relate the idea of a z-score and the idea of a percentile to working with the normal curve. We're going to find area under a normal curve. Well, suppose that we have a random variable that's normally distributed with mean mu and standard deviation of sigma. Then what it turns out is that the z-score that we just calculated is also normally distributed, but it has a mean of 0 and a standard deviation of 1. And this random variable is said to have the standard normal distribution. Why is that important? Or why is this formula important? What this tells us is no matter what the mean and standard deviation are for the normal curve, there is a way for me to standardize that by looking at the number of steps I am away from the mean, where the step size is the standard deviation. So it allows me to reduce everything to this common measurement level of a z-score. The benefit of that is calculating area under a normal curve can be complicated. But the standard normal curve is one where mathematicians and statisticians over the years have tableized that. So what they said was, since we can reduce everything to the standard normal case, what we're going to do is we're going to make a table of values that will give us probabilities for the standard normal curve, and we are going to use this z-score to help us use that information for any normal distribution. So the standard normal curve looks like what we've been looking at before. It's centered at 0, and step sizes are 1 and -1. The table that we're going to use, called the normal table, will actually give us the value then of the zth percentile, or it'll give us z, the value z, and the value in the table is a percentile, so it's the percent of the data that falls below this score. So in the normal table, we will get the probability of being less than or equal to z. So for example, let's say that IQ scores are modeled with a normal distribution with a mean of 100 and a standard deviation of 15, and an individual whose I-score is 120 would be 1.33 standard deviations above the mean. We'll take 120, the observed value, minus the mean of 100, divide by the standard deviation, and we'll round to 2 decimal places, which gives us 1.33. So that means that this is an above average IQ, and it's 1.33 steps above the average. If we go into a normal table, the normal table has values down one column and across the top. And what it does is it gives me the z-score to 2 decimal points. What goes down this first column are the integer value and the 10th digit. What goes across the top is a 100th digit. So if I want the z-score for 1 point, or if I want the probability to go with 1.33, I would look at the row for 1.3 and down the 0.03 column, and where they intersect is the value I'll pull out of the table, which is 0.9082. So what that means is that if I were to draw this curve, I've got my 100 as my mean, and my step sizes are 15, and I put 120 on there. If I shade to the left of that region, or the left of that line, 120, the shaded region represents 90.82% of the area under the curve. So in other words, a score of 120 is at the 90.82 percentile, excuse me, the 90.82 percentile of the distribution. 90.82% of the population will have a score less than or equal to 120. Or equivalently, if I pull somebody at random and I measure their IQ, there's a 90.82% chance their score will be less than or equal to 120. There's only a 9.18% chance that their score will be more than 120. Or equivalently, there's only 9.18% of the population that will have a score above 120. So this is an example of how we can use that z-score to come up with a probability, right? We can take the curve that we were given, we can change it to a value for z. We can then look that up in a table, and that gives us a context for this area. Now, if you look at the normal table, which we'll show you a full copy of it here as well, there is one in the back of the book or available on MyStatLab. And I'll also try to post a copy of it. You can see that we actually have 68.26% of all data points lie within one standard deviation. And we have a little more than 95% lie within two standard deviations. And from there, we just kind of fill in the rest of it. So let's do an example. Let's find the area under the standard normal curve to the left of z equals minus 0.38. Well, remember that the table gives us the probability to the left of a number, and it's a standard normal curve with a mean of 0 and a standard deviation of 1. So knowing that z is minus 0.38, I'm going to go to my table. I'm going to look down the z column until I see minus 0.3. I'm going to look across the top row till I see 0.08, and I'm going to see where those two, that row and that column intersect, and I get 0.3520. So in other words, there's a 35.2% chance that I would get a z-score less than minus 0.38. The area to the left of z equals minus 0.38 is 0.3520. Again, the table gives me the probability being less than this z value. If I wanted the area to the right, I'm going to use the complement aspect of it. That the area under the curve completely is 1. The table gives me the area to the left. So if I want the area to the right, I will take 1 minus the area to the left. We saw that up here. Right? The table gave me a value of 0.9082. That was the area to the left of this value. What's left over on this side of it is to the right of that value, and it's 1 minus the area to the left. Okay, so let's find the area under the normal curve to the right of z equals 1.25. Well, if I go to my table, I can look down the z column till I get to 1.2. I can look across the top until I get to 0.05, and I'm going to see where those cross. So I'm going to look across 1.02. I'm going to look down 0.05. And I'm going to see where those intersect. So I get a value from my table of 0.8944. And I have this value of 0.8944. Well, what does that represent? That says that the area to the left of 1.25 is 0.8944. To get the area to the right, I'm going to have to take this value away from 1. So to get the area to the right, I'm going to take 1 minus 0.8944, which gives me 0.1056. Again, the table gives me the value to the left, so it would say 89.44% of all data points lie to the left of 1.25. The other 10.56% lie to the right. Okay, what if I want to find the area under the standard normal curve between z equals minus 1.02, and z is 2.94. Well, we'll do some more examples of this in a bit when I can draw a picture. But the area between two values is the same thing as saying, okay, let's find the area to the left of the larger one minus the area to the left of the smaller one. If we use our table, we would come up with these two values, so the area between those two is 0.8445. Again, we will illustrate this later on with the normal table. So there's a couple different types of ways that we can run into a problem. One is that it gives me a normal distribution and it says find the area to the left of a particular value. How I'll do that is I'll first convert it to a z-score. I'll then use the table that I'm given to find the area. So I can either use technology, which there are many tables in StatCrunch or Minitab. Excel has it. Your calculator may also do it. But we're going to work with just the table at this point. To find the area to the right, we'll go through the same process. We will first convert the value to a z-score. We'll then look it up in the table so that we can see what the area is to the left of x. We'll then take that away from 1 to get the area to the right. And if I want the area between, I'll take the area to the left of the bigger one minus the area to the left of the smaller one. Right? Notice if I were to take the area to the left of x2 here, that would shade this entire region, including this piece down here. Well, I want to exclude that piece. That happens to coincide then with the area to the left of x1. So by removing the area to the left of x1, I get the area between those two. And now we're going to look at finding the value of a normal random variable. So one application of that normal table is to, given a mean and a standard deviation, find the probability of observing a particular value, either less than or greater than that value. The other is to say, given some observation and a mean and a standard deviation, or given some percentile and a mean of standard deviation, find a threshold that would go along with that. So we're going to draw a normal curve. We're going to shade the area corresponding to proportion, percentile. We'll use table V to find the z-score that corresponds to that area. We'll then obtain the normal value by going backwards and getting x equals mu plus z times sigma. We've been using this formula to find z. So we are given information about the observed value, a mean, and a standard deviation. We're calculating a z-score, then looking that z-score up in a table and finding a probability. The other way we can do it is give you a probability. From that, we can determine a z-score. Knowing the mean and standard deviation, I can work backwards to find a value for x. And the formula for finding that value for x is mu plus z sigma. So for example, let's say that the combined score on the GRE is normally distributed with a mean of 1,045 and a standard deviation of 189. We want to know what the score of a student whose percentile rank is at the 85th percentile. Well, what does the 85th percentile mean? It means that 85% of the scores lie to the left and 15% of the scores lie to the right. So what I want to do is look in the body of the normal table and try to get as close to 0.85 as I can, because the values in the body of the table are the percentiles. They're the percent of data that lies to the left of a z-score. If I look that up, I get a z-value of 1.04. I know that the mean was 1,049 and that the standard deviation was 189. So I can put that in. 1,049 plus 1.04 times 189 is 1,246. So a score of 1,246 would put me in the 85th percentile. So again, a person who scores 1,246 would rank in the 85th percentile. Well, why is this even useful? Think about a diagnostic test for a disease. Most of the characteristics we will see in a population will follow a normal distribution. If I know from studying those characteristics what the mean and standard deviation are of that population, I can come up with a way of diagnosing a disease just by looking at specific values. Maybe I think that there's going to be a problem if I'm more than 2 standard deviations away from the mean. Well, let's take diabetes, for example. Let's suppose that the average blood sugar score is 100 and that we have a standard deviation of 10. I'm going to diagnose somebody as being diabetic if their blood sugar score is more than 2 standard deviations away. And I'm going to diagnose them as, I think it's hypoglycemic if their score is more than 2 standard deviations under. Well, a score of 120 then, anything above 120 would indicate that the person is likely diabetic. Anything under a score of 80 would indicate that the person might be hypoglycemic. Rather than having to take a blood sample, measure their sugar level, and convert that to something with the normal distribution, we've used this method of finding a value to give us a range of what we would consider a standard or what would be considered in the range of wellness. I don't want to use the word normal because I don't want to confuse the two. Anything where we had a blood sugar score of between 80 and 120, we would consider to be okay. Now, again, that's not exactly how diabetes works. I think currently if you have a fasting blood sugar of more than 100, they classify you as pre-diabetic. And if you have a fasting blood sugar more than 120, then they diagnose you as diabetic. But it was just an illustration of how utilizing that test can help us out. Here's another example of where it might be useful. It's known that the length of a certain steel rod is normally distributed with a mean of 100 centimeters and a standard deviation of 0.45%. Suppose that the manufacturer wants to accept 90% of all rods manufactured. Determine the length of rods that makes up the middle 90% of the steel rods manufactured. Here I have, in this case, I've got a tolerance. They need to be made to a certain spec. If I get too far away from that spec, it's not going to be something that can be utilized. So I'm going to determine where the middle 90% lie here. In order to do that, the middle 90%, I'm looking at 5% above and 5% below. So that would mean 5% is above this point would be 95% lies to the left of that point. So if I were looking at x2, the value there would be the value that is at the 95th percentile of the standard normal curve, which happens to be at 1.645. This point would be at the 5th percentile of the standard normal curve, which is at minus 1.645. Because this is symmetric, these are the same number of standard deviations away from the mean, just one's going upward, so it's positive, one's going downward, so it's negative. But what I need to do now is find the links that correspond to these two z-scores. So I'm going to take the mean and add on this first z value times sigma, giving me 99.26 centimeters. And I'll do the same thing for the other one, giving me a length of 100.74 centimeters. So as long as the rod that comes off the line is between these two values, I'll accept it. If it's outside those values, so if it's smaller than 99.26 or more than 100.74, then it's too far out of my range of tolerance and I'm going to reject accepting it. So the interpretation is that the middle 90% of all steel rods have links between 99.26 and 100.74. This leads us to some notation that we're going to need to have as we move forward. And it's called Z sub alpha. So Z with an alpha as a subscript. Z sub alpha is the z-score that corresponds to the place on the curve where alpha percent of the area lies above it. So in other words, take for example, let's take for example on our last slide, 5% of the area lies above this point. So this 1.645 is actually Z sub 0.05. Right? Because 5% of the area lies above that value. This would have been minus Z sub 0.05. We tend to work with Z sub alpha being with positive numbers. The corresponding negative value would be negative Z sub alpha. 5% lies to the left, I'm going to get a negative Z value, and so we'll call it minus Z sub 0.05. So again, this one would be minus Z sub 0.05. Okay, so that ends our discussion of the normal curve. I'm going to go through some examples and try to show you some more examples of how to calculate the normal curve and work with finding probabilities as well as working backwards. So go on and look at the examples, and we will in your next presentation.